Hello everybody, welcome to my basement. Let's dive right in. We're going to start with chapter 20, and chapter 20 is all about electrical charges and electric forces. And electric charges and electric forces is such an interesting topic, and it just surrounds us every day. Every aspect of our life is impacted by electrical charges and forces. It's electrical forces that hold atoms together, that keep the electrons winging around the nucleus, so that we have, everything. It's electrical charges that are responsible for all the electronic devices that surround us, from our cell phones / mini computers that we carry in our pockets, to the computer that I'm using to record this lecture, to the toaster that toasted my bread to a lovely golden brown this morning for breakfast. Electrical forces and electrical charges surround us. Now, has anyone ever seen an electrical charge? When I say the word electrical charge, I'll bet you don't freak out about it too badly. It's not too scary of a thing. It's a word we've heard before, but what is it, and have you ever seen one? And the answer is no. We've never really seen an electrical charge. Why? Because they're carried on subatomic particles that are too small for the human eye to see. And so what we're going to be talking about in the beginning of this chapter is the charge model. We're going to observe some phenomena, and then we're going to talk about how can we describe this phenomena with what we call the charge model. So probably most of you have seen some static electricity in your life. If you've ever seen a lightning strike, then lightning is a huge discharge of static electricity. Now, you can create a little static electricity with a balloon. Maybe some of you have done this before. Here we go. Okay, we're getting her going, getting her charged up real good. Oh, okay. Just looks like I need a shower. Okay, here we go. I got some little pieces of paper here. Let's see what happens when I bring them. Oh my goodness, that is exciting. Oh my gosh, look at that. Woo! Some little pieces of paper here. Let's see what happens when I bring my charged balloon. Whoa, look at that. They all flew up onto the balloon. That, people, that is exciting. Okay, so we saw that the balloon could attract some tiny pieces of paper. What force could be responsible for that? Any of the forces we learned about last semester? Gravity? No. Friction? No. Tension? No. None of the forces that we talked about last semester could possibly explain why those little bits of paper jumped up onto the balloon. Here's another example of some surprising forces that maybe we haven't seen before. Here I have two pieces of tape. Oh, and look at that. Oh my gosh. I have specially prepared them. They are very attracted to each other. That's interesting. And I might note that this is not simply the sticky stuff sticking together, right? The sticky stuff is facing out, and they just want to come together. Why? There must be some force at work. Now that's interesting. Here it's an attractive force bringing them together. And now here's two pieces of tape. And what kind of a force do we see here? They're pushing away from each other. They really do not want to be next to each other at all. So we've seen that this force, this whatever we're calling it, this force can be attractive or it can be repulsive. So today, our goal is to talk about the charge model. So these are the goals for chapter 20. We're going to talk about the charge model and how the charge model can explain the forces that we observe, like what we just demonstrated. And we're going to talk about how these forces give rise to the structure of the atom. Just scratching the surface on this one. We'll come back to this many times throughout the semester. And we're going to talk about a couple of other ways to sort of wrap our brains around this force that we've observed in a little bit more of an analytical way. Coulomb's law is the name of the mathematical equation that we'll use to calculate these numbers. And then we'll introduce the idea of the electric field. The electric field is something that permeates space around a charged object and causes other charged objects in the vicinity to react. So, electrical charges, let's go to a simulation here. And I think this will help us to see what was happening when we charged up the balloon and used it to attract the pieces of paper. So here we see this simulation, and I've got this balloon. And I guess one thing to note is that there's charges everywhere. Right? I mentioned that it's electrical charges that hold atoms together, that hold the structure of atoms together. And if you've ever had any kind of a beginning chemistry course, then you've learned this. You've learned that protons live in the nucleus and they're positively charged. And electrons wing around the outside of the nucleus and are negatively charged. And so if I ask, are there positive and negative charges in any object, say me, then the answer is, of course, yes. In any neutral object, even if an object does not have a net electrical charge, it still has a whole bunch of charges. Any object you can pick has billions and trillions and gazillions of positive and negative charges, because all of the electrons in this pencil have a negative charge. All of the protons have a positive charge. So that's what we see in the simulation. Now, obviously, the simulation is not showing all of the charges in this sweater, but it's showing that even though the sweater right now is neutral, it's neutral because it has equal numbers of positive and negative charges. It's not neutral because there are no charges at all. That's the important thing to note here. So, if I come over here and I rub some charges off, then my balloon becomes negatively charged, and my sweater becomes positively charged. Not surprisingly, they attract each other. Opposites attract. Okay, well, that's lovely. What happens if I bring it over next to the wall? Notice the wall is neutral. So, will the balloon have an effect when it goes to the wall? And the answer is, yes, it will. Whoa! The balloon is attracted to the wall and the sweater, both. Now, it's attracted more strongly to the sweater because the sweater is purely positive. But the balloon is also attracted to the wall. And we see why, because the balloon is negatively charged. The balloon pushes the negatives in the wall farther away. The positives are then closer. We have attraction between opposites, repulsion between likes. The balloon sticks to the wall. This is analogous to what happened when I picked up the little pieces of paper with the balloon. Okay, let's go back to the lecture slides here. After rubbing the balloon on the sweater has a positive charge. Why? Is it because electrons move to the balloon? Is it because protons move to the balloon? Is it because electrons moved off the balloon? Or is it because protons moved off the balloon? Why don't you think about it for a second, pause the video, and then when we come back, I'll show the answer. Okay, welcome back. So, indeed, what moved here was the electrons. It was the electrons that moved off of the balloon. Or excuse me, it was electrons that moved off of the sweater and onto the balloon, giving a net charge of positive to the sweater and a net negative charge to the balloon. And in general, this is true. In general, it is the electrons that move, that give something a charge by rubbing. And it is not the protons. And we say, why? Well, because the protons are tightly bound within the nucleus of the atom. And we're not just going to rub a proton out of the nucleus of the atom. In fact, if you pull a proton out of the nucleus of an atom, that is called a nuclear reaction, which I'm not going to demonstrate in my basement. Not this week. Maybe next week. Okay, so in general, objects acquire a positive charge by losing electrons. They acquire a negative charge by gaining electrons. So one way or another, it's the electrons that move. And why? Again, it's because the electrons are on the outside of the atom. They are not tightly bound within that nucleus. A little bit of terminology here. A conductor is a material that charge easily passes through, and an insulator is a material on which charge is immobile. And so our usual examples of insulators are things like plastic and wood. In plastic and wood, the electrons are bound to individual atoms, individual molecules. They cannot travel throughout the material, transferring electric charge. A conductor, typically, is a metal. And in a metal, those charges can move freely. And so, in a piece of metal, charges can move freely, carrying charge and current, a topic we'll come to in a couple of chapters, but that makes a metal a good conductor. And it's the same thing that makes it a good conductor of heat, also, as we learned about last semester. Those electrons can carry kinetic energy, which makes the metals good conductors of heat. They can also carry charge, which makes them electrical conductors also. A little bit of terminology there. Now, this chapter is all about electrostatic equilibrium. In other words, electrostatics, in other words, static electricity. In other words, charges that are not moving. Now, we might look at this and say, oh, well, yeah, but when you rubbed the balloon, didn't you move some charge? And the answer is absolutely yes. So we rubbed the balloon, we got it a little bit charged up, and then now we're talking about it, right? So that's what this physics is about. It's like, okay, maybe we made a few changes. We let things settle down. Now we're going to talk about it. So that's what we're in this chapter. We're going to talk about when charges start moving in a couple of chapters. That's called a current. And that's a word you've probably used before, but we're going to kick that down the road for a couple of chapters. Okay, I want to show you something interesting here. And then we'll talk about why I have. Okay, so I've got here my magic wand. Okay, it's a piece of PVC pipe. I'm going to rub it on my sweater. And then I'm going to use my magic wand to do magical things. Oh, come to me. Come to me, Ken. Oh. Okay, so I hope you were impressed. I was personally pretty impressed. What happened there? I gave a charge to the magic wand, the piece of PVC pipe. That's what I gave an electrical charge to. How then did it attract the aluminum can, which did not receive a charge? Good question, Ansel. I'm glad you asked it. Well, I've got a little diagram here that can help us understand. Here we have a neutral metal object. There's equal numbers of positives and negatives. Of course, we know there's a gazillion negatives and a gazillion positives, but there's equal numbers, which makes it neutral. Now, I bring next to it a positively charged rod. The negatives in the sphere are attracted to the positives in the rod. Well, the positives are repelled. Now, I had to say it was a metal sphere because in a metal sphere, a metal is a conductor and charges are free to move. The charges separate. The negatives get as close as they can to the other positives in the rod, and the positives in the sphere get as far away as they can. Now we have a force of attraction between negatives here and positives here. We have a force of repulsion between positives here and positives here. But the negatives are closer, so they win. And we have a net attraction, as I just showed in that demonstration. Okay, let's do a quick example. Two conducting spheres are touching each other. A charged rod is brought near, as shown in the picture. The spheres are then separated using insulated gloves, and the rod is taken away. After the charged rod is removed, what is true about the spheres? And I guess I'm asking about their charges. Will they both be positive? Will B be positive and A neutral? Will A and B negative and B is positive? Or will they both be positive? Why don't you pause the video and see if you can't figure this out. You may want a picture to help you work through it. So the charges are free to move. Since they're touching, they're free to move from one sphere to the other. So where will the negatives go? Well, the negatives will try and get as close to these positives as they can, and the positives will try and get as far away as they can. So that's the situation with the rod brought near. Now, I'm going to use my insulating gloves to come in over here and separate these two spheres just a little bit. Now they are separated, they are no longer touching, and I take my rod away. What happens? Well, I have A is positive and, A is negative and B is positive. And so the answer we reach is that A is negative and B is positive. And so we've charged these spheres, interestingly, without rubbing them or hooking them up to a battery or anything like that. This is called charge by induction. So the charge model then is that charge is an intrinsic property of matter. It is carried on subatomic particles, protons and electrons being the ones we will talk about the most. We measure charge in coulombs. It turns out a coulomb is a very large amount of charge. A lightning bolt might release 15 to 100 coulombs, which is quite a bit. It's probably only a few microcoulombs of charge that I was getting on the balloon that I rubbed. You know, a battery can hold actually a surprising amount of charge. A AA battery can hold something like 5,000 coulombs. So, and what else about charge? Charge is an intrinsic property of some types of matter. What does that mean? Well, electrons have a negative charge. Why? I don't know. They just do. That's what I mean. It's an intrinsic property of electrons to have a negative charge. Just like it's an intrinsic property of electrons to have a mass of 9.11 times 10 to the negative 31 kilograms. Why does an electron have that mass? I don't know. It just does, right? So charge is an intrinsic property of some types of matter. The other thing about it is it can come in positive and negative. There are two types of charge. And if something's neutral, it doesn't mean there's no positives and no negatives. It means there are approximately equal numbers of positives and negatives. In the next video, we'll introduce Coulomb's law. Coulomb's law is an analytical tool for calculating forces on electrical charges.